Okay, so project 5 due today. Give me that before you leave. Quiz 4 is due Wednesday. And Friday, there's no classes, right? Final exams start on Thursday. Thursday, Friday, Monday, and Tuesday are final exams. Our final exam is on Monday, the 19th from 8 to 10. But I will be here also 10:30 to 12:30, so you can stay a little bit later or come a little bit later if you want. But make sure you allow yourself 2 hours. Don't show up after 10:30. Okay, so last class we did a word problem that involved mixing, right? It was a mixture problem with salt water. And today we're going to continue to look at some word problems that involve differential equations. So lots of things grow or decay at a rate proportional to their amount or size. And that leads, meaning like the bigger the population, the faster it grows, right? Because there are more members of that population to reproduce. So that leads to a differential equation of the form dy dt equals k times y, right? That's what grow proportionally means. When two things are proportional, one is a constant multiple of the other. So the rate of growth is a constant multiple of the size of the population. So k is just a constant. It's called the constant of proportionality. All right, so we could generalize further and also assume that a constant amount is also added or subtracted from the population each period. So that would lead to a differential equation of the form dy dt equals k times y. So the rate of growth is proportional to the size of the population, plus or minus some constant that you are also adding each period or subtracting. So for example, a scholarship fund earns a continuous interest rate of 8% of the current balance each year. So let's write a differential equation of the form dy dt equals ky plus or minus a. All right, so if it grows at 8% of its current balance, so its growth rate is how it grows. So it grows at 8% of its current balance, right? And then what is plus or minus a? What does the a represent here? Yeah, deposits or withdrawals, yeah. Okay, so what if $1,000 is withdrawn per year in a continuous way so that we can just put it into this differential equation? So now I'm going to have dy dt is equal to 0.08y. So the rate of the change of the account is 8% of the size of the account plus minus $1,000 because we're withdrawing 1,000 each period, each year. So in this last scenario, how much money would need to be in the account for this to be stable? So this is actually a real, like if there's a scholarship fund, they give out $1,000 every year, right? So how much money needs to be in this account so that the 8% growth rate balances the $1,000 award? So for an account to be stable, that means its rate of change would be 0, right? So it's not growing and not shrinking over time. So dy dt is what represents the rate of change. So if I make my rate of change 0, then whatever size y makes that rate of change 0, that's the amount of money in the account that will make it stable where I can withdraw $1,000 a year without changing the size of the balance. So I just solve this for y. $12,500. Okay, so with a balance of $12,500, it's earning 8% interest and withdrawing $1,000 a year. The balance will just stay at $12,500. without gaining or losing any money. All right, so here's another one. Dead leaves accumulate on the ground in a forest at a rate of 3 grams per square centimeter per year. At the same time, they decompose at a continuous rate of 75% per year. What is an equation for the total quantity of leaves at time t? Okay, so first we should define a variable to represent the total quantity at time t. All right, so they're telling me about the rate at which these leaves accumulate and decay. Right, so both of those things they gave me are rates, so I'm going to use dq dt. So what's the rate at which they accumulate? Overcomplicating. 3. Yeah, so Ryan said 3t. He was making a common mistake in trying to jump directly to the formula for Q, right? 3 is the initial quantity? Yeah. Oh, no. Oh, yes. A would be the 3, yeah. Constantly adding a constant amount each year. Yep. Yeah, and so if you did 3 times t, you could figure out how much had accumulated at any given time, but since I'm trying to write an equation for the rate, I don't need to do the times t. So this is just going to be 3. That's the rate at which it accumulates. And then I'm going to subtract the rate at which it decays, right? Because how much the rate that it's accumulating is going to be the rate it accumulates minus the amount that decays, the rate it decays at. Okay, so it's decaying at a continuous rate of 75% per year. So that's going to be times 0.75 of itself, minus 0.75 Q. Okay, so they asked for an equation for the total quantity at time t, so I think that means I'm supposed to solve this. I think you should take a couple minutes and practice your separation of variables technique and solve it. And also you can try to find the equilibrium solution. What quantity of leaves will just eventually make it so that the amount of leaves on the forest floor is always the same. Okay, so my hint was to factor out the negative 0.75. You do not have to. It just makes the integration piece a little bit easier when you get there. So if I'm going to separate this so that all my Q's go together and all my non-Q's, my T's go on the other side, I'm going to divide both sides by Q minus 4 and and multiply both sides by dt. And then I can take the integral of both sides. So what is the antiderivative of 1 over Q minus 4? The ln of Q minus 4. And the reason that integral was not as hard as if you didn't factor out the negative 0.75 is that if I were to take the derivative of the ln of Q minus 4, you get 1 over Q minus 4 times the derivative of the inside, which now is just 1, right? Because there's no coefficient on Q. All right, and then the negative 7.5 becomes negative 7.5 t plus a constant. And then how do you solve this thing for Q? We need an equation Q equals some stuff with t in it. Exponentiate, raise both sides, raise e to both sides. Oh yeah, sorry, thanks. 0.75. So e to the ln of some stuff is just the stuff, because e and ln are inverse functions. E to the x and ln x are inverses, so I just get my q minus 4 equals e to the negative 0.75 t times e to the c. And I forgot the 5, sorry. And e to the c is just another arbitrary constant, because e is 2.718 raised to an arbitrary constant gives you another arbitrary constant. Move the 4 over, and you have an equation for q. And then that's a general equation, it's a whole family of solutions that will make the differential equation true. One of those solutions is the equilibrium solution. And you can get that by setting the derivative dq dt to 0. So that was 3 minus 0.75 q equals 0. This is the solution where nothing ever changes. It's a constant solution where the amount of leaves on the floor is just going to stay the same all the time, because the rate at which you add leaves equals the rate at which the leaves decay. And you solve this thing and you get q equals 4. Okay. Is that compatible with this family of solutions? What constant c in the family of solutions gives you this solution? 0. Yeah. So this is just one particular member of that family corresponding to a constant c equals 0 in this case. All right, we're going to skip the challenge and look at Newton's law of cooling. All right, so Newton's law of cooling states that the rate of change in the temperature of a body is proportional to the difference between the temperature of the body and the external pressure, temperature. All right, so let's use this fact to answer this question. A roast is taken from the refrigerator where the temperature is 40 degrees. So we're going to assume that the roast is 40 degrees. It's been in there for a long time, and it's the temperature of the refrigerator. And we're going to put it into a 350 degree oven. 1 hour later, the meat thermometer shows a temperature of 90 degrees Fahrenheit. If the roast is going to be done when the temperature reaches 140, what is the total time the roast should be in the oven? All right, so Newton's law of cooling. The rate of change in the temperature is proportional to the difference between the temperature and the external temperature. So let's see if I can write a differential equation. Rate of change of temperature. So I need a variable to represent temperature. What do you want to use? T, maybe capital T, because we have also time in here. We'll use little t, and we'll just be careful to differentiate. The rate of change of the temperature with respect to time is proportional to, so that means it's a constant multiple of, K times the difference between the temperature of the thing, the body, and its external temperature. So we'll just call this difference, right? Maybe with a little sub-zero to mean the difference at time 0. All right, so for my roast example, I've got dt is equal to K times what's the initial temperature difference between the roast and the oven? 310 degrees. The roast starts at 40 degrees, put in a 350 degree oven. The difference between those two, I'll just actually write this out, is 310 degrees. All right, so that means dt is 110 K. All right, and then an hour later, the meat thermometer shows a temperature of 90 degrees. So we're given a temperature at time t. So what I really need is a formula for temperature at time t so that I can plug that stuff in and get the K. So how do you solve this thing to get a formula T, capital T, with respect to time? I can separate and solve. Yep, so we should multiply both sides by dt, little d little t. So I have capital DT equals 110K, which is just a constant, DT. Yes, thank you. Good question. K represents like an insulation factor, right? For like some ovens could okay, so there are ovens that are advertised right now that can boil water in 90 seconds, right? So like but some older ovens or like a Bunsen burner, right, can't do that. And K is sort of a factor that talks about the efficiency of the oven. So it's not the same for every oven. So if I cooked a roast, needed to take a roast from 40 degrees to 140 degrees in my oven, it might take 3 hours. In somebody else's oven, it might take 3.5 hours. So K is a constant that talks about the specific oven.
So the reason, I'm curious why we used the K here, but we didn't in the last one. How does it say proportional?
Yes. So in the last one, we knew the constant of proportionality. So I didn't actually use the word proportional, but the 75% was the K. Yeah. And in this one, whenever you see a word problem with, proportional, it just means one's a constant multiple of the other. Sorry. There we go. All right, and then we integrate both sides. So the antiderivative of d capital T is capital T. The antiderivative of 310K d little t is 310K T plus C. Sorry, I did this wrong. I didn't finish writing down the equation. It's proportional to the difference in the external temperature. Okay, so the temperature of the body is a changing quantity, right? It's not, otherwise it would be a constant rate of change, and that's not true. Okay, so I've got Newton's law of cooling interpreted wrong. Okay, the difference between the temperature of the body, which is a changing quantity represented by capital T, and the external temperature, right? And the external temperature that we're putting this roast into is 350 degrees. So that is the difference between the temperature of body and the external temperature. And maybe it would make sense to do 350 minus T, because 350 is the larger quantity. Though when I solve this thing, I'm going to end up putting that in absolute value because I'm going to take an ln. So it doesn't really matter. But if you like to do things that make sense, right? I like to do the subtraction so that the answer is positive. All right, that is much better. Now we have to solve this. Okay, so I'm going to separate by multiplying both sides by dt and dividing by 350 minus t. Then integrate both sides. And the antiderivative of 1 over 350 minus t is the ln of 350 minus t times -1 because of that -1 on the t in the chain rule. So that equals kt plus c. Raise e to both sides. And well, maybe I should have moved the negative over first. Just divide both sides by -1. Then raise e to both sides. Okay, so we get 350 minus t equals e to the negative kt times e to the c. And e to the c is just another arbitrary constant. So I have c e to the negative kt. I'm going to subtract 350 from both sides. And that's negative t. So t is 350 minus ce to the negative kt. All right, now I have two arbitrary constants in this, well, I have two unknown constants in this, right? I have c, my arbitrary constant that came from integrating, and I have k, which we just talked about represents the efficiency of the oven that you're working with, right? So if I have two unknown constants, I need two pieces of information to be able to solve, right? If you have one, you just plug in your given information, solve for, but I have two. So do I have two pieces of information that I can plug in to solve for those two? Yeah, I have a temperature and the time it takes to get to that temperature. So I have 1 hour should give me 90 degrees. Do I have any other ones? Maybe temperature times 0 is 40 degrees. Yeah. So T of 0 should be 40 and T of 1 should be 90. So T of 0, if I put in a 0 for T, this is just going to give me 350 minus C e to the 0, which is just C, equals 40. And T of 1 says 350 minus C e to the negative k has to be 90. So this one I can solve for C, and I get 310. And then now I can replace this C with a 310 and solve for K. Okay, so I just want to isolate the e to the negative k. So I'm going to subtract 350 and then divide by negative 310. So I get e to the negative k is approximately 0.8387. Then what do? Take the ln of both sides. So negative k is equal to the ln of 0.8387. So I get negative 0.175 is negative 0.176, we'll call it. Which means K is 0.176. All right, so now I know C and I know K, I can write a final formula for temperature at time T. So my temperature at time T, it's this formula right here, but now I know what C and what K are. So this is 350 minus 310 e to the negative 0.176 t. So that's my formula. And then the question was, how long till I reach 140 degrees? So plug in 140 for temperature and solve for T. So 140 minus 350 divided by negative 310 So e to the negative 0.176 t is 0.677. Take the ln of both sides. Oops. Negative 0.389. And then divide both sides by the negative 0.176. 2.2 hours approximately. All right, so Newton's law of cooling. This was how we translated it into a differential equation. I want you to do this again, right? Use Newton's law of cooling to solve this murder mystery. All right, so let's solve this together. Here's my differential equation. The rate of change of the temperature of a body with respect to time is proportional to, that means is a constant multiple of, the difference between the temperature of the body and the surrounding temperature. So we're using capital T to represent the temperature of the body, so we do that minus 68, which is the temperature of the room. And it's a personal preference. It is not going to matter in coming up with the final answer, whether you did T minus 68 or 68 minus T, right? Because when you're doing this, the negative will eventually cancel with something else, or you'll take an absolute value. So you can do it either way. It doesn't matter. So I want to separate this so that I get T's on one side, capital T's on one side, and little t's on the other, and then integrate both sides. And if you had also moved this k over to the left, that would be fine also. But when you'd integrate, you'd have a coefficient on the t, which means you'd have to account for the chain rule. So the antiderivative of 1 over t minus 68 dt is the ln of t minus 68. And because the coefficient on t is a 1, I do not have to compensate for the chain rule, right? Otherwise, I would have to divide by that coefficient on t. And that should equal kt plus c. Then we exponentiate and take e to both sides. And we end up with t minus 68 equals e to the kt times e to the c. And e to the c is just another arbitrary constant. So my final equation is going to be t equals c e to the kt plus 68. All right, so then I have two unknown constants in there. To find out what they are, I need two pieces of other given information from my equation. So if we call time 0 the time of discovery, what was the temperature of the body? 90.3. So if I plug in a 0 for time, for little t, I get c e to the 0 plus 68. That's supposed to equal 90.3 degrees. E to the 0 is just 1, so c is 90.3 minus 70 would be 20.3, and subtract 2 more, so 18.3. $22.3? Oh, yeah, right. Okay. And then capital T of little t, right? Temperature at time is now 22.3 e to the kt plus 68. And then to find out what k is, I use my other piece of information, that 1 hour after we found the body, so t of 1, t at time 1, that's going to be 89. So 22.3 e to the k equals, plus 68 equals 89. So then we solve for k. So 89 minus 68 divided by 22.3. So we get e to the k is approximately 0.9417, which means k is the ln of that number. And I get negative 0.06. I'll just use that, even though it's not exact. Yeah. So if I had done 68 minus t, I would have had my formula would have come out with negative kt, and when I solved for k, it would be positive, right? So, but when I did it this way, I came out with ce to the positive kt, and my k came out negative. Either way, your final formula is going to come out ce to the negative 0.06 t plus 68. Oh wait, and I know c now. C is 22.3. So yeah, either way, it's just that the constant that you solve for will come out positive or negative, and your formula will either have a positive or negative here, and so either way, you'll end up with negative 0.06 t in there. All right, so that's my final formula for the temperature of the body at time t. So now I want to know how long ago the murder occurred. So what is the temperature at the time of death? 98.6. So we replace capital T temperature with a 98.6, and I want to solve for little t. All right, so we've got 98.6 minus 68 divided by 22.3. Okay, so then I take the ln of both sides. And divide by negative 0.06. And I get negative 5.27. Why did that come out negative? Prior to 9 a.m. We called 9 a.m. times 0, and the murder happened before that. Okay. So this says about 5¼ hours ago. And if I wanted to be really precise about it, I would say 0.27 of an hour. Oops, 0.27 of an hour is 16 minutes, right? So to the nearest minute, 5 hours before 9 a.m. would be 4 a.m. plus an additional 16 minutes before that would be 3:44 a.m. Okay, does this make sense? Good. Okay, so that's all I have for today. That's our last topic of the semester. You have some things to work on. You've got quiz 4, though you're not supposed to talk to each other. If you're going to work on that, you have to be silent. And you have a study guide for the final exam that you can spend the rest of class on. And your project 5 is due today. If that, for some reason, isn't done, you've got 15 minutes.